In today's lecture, I'm talking about Faraday's law and Lenz's law, which is associated to the Faraday's law. Look at this figure. Uh, this is a bar magnet, and this one is a loop, current carrying, not a current carrying loop, but conducting loop. This is a complete circuit connected to galvanometer. So, in this first case, the velocity of this bar magnet is zero. So, this is not moving. And this current loop, that is the conducting loop, is also not moving. If both of them are not moving, we can't see any induced current in galvanometer, right? No motion between magnet and loop. In second case, you are moving this bar magnet towards this loop. Because of this motion, what is happening is the magnetic field lines are increasing. That is, magnetic field lines passing through the surface of this loop is increasing. That means magnetic field is getting stronger than before. In this case, the current is induced in the loop, which can be seen in this galvanometer. You can see certain reading in the galvanometer. On the other hand, when you move this bar magnet far away from this current loop, what is happening? The direction of induced current is just opposite to the previous case, this case, right? The only difference between this and this is the direction of induced current is just opposite to first one. Okay, from this experiment, what we conclude is when a magnet is moved near a conducting loop or take away from the conducting loop, a current is induced in the loop. When you stop the motion of bar magnet, current also stops. Okay, what happens if you move a conducting loop in the direction of magnetic field? Does it still produce induced current or not? It's not, because there is no change in magnetic flux when you move a loop in the direction of magnetic field. Okay, so from these discussions, what we conclude is that the current is induced only when the magnetic field through the loop is changes. If there is no change in magnetic field lines, then induced current will also not be generated in the circuit, in the conducting loop. Okay, so an induced EMF is produced in a loop or a complete circuit whenever the number of magnetic field lines passing through the plane of the loop is changed. If there is no change in magnetic field lines through the surface of closed circuit or conducting loop, induced current will not be produced. When there is change in magnetic field, induced current will be produced. This is the conclusion. So, changing current in one loop can also induce a current in a second loop. Look at the side figure here. In this figure, we don't have any magnet, but there is a current passing through this first loop, right? Because of this current, magnetic field is produced. We discussed about electromagnetism, that is electricity and magnetism are two facets of same coin, right? One thing can produce another. So what is happening in this figure is there is this current, you are increasing the current, and then because of increasing current, magnetic field lines are also increasing. That means in this second loop, magnetic field lines are increasing. That's why there is an induced EMF, right? It is shown here. If you decrease the current in this loop, by doing so, magnetic field lines are decreased. What will happen then? Current will be induced in second loop in opposite direction than the previous one, right? So based on these explanations, we can explain Faraday's law. Before doing so, we have to define magnetic flux. The magnetic flux is defined by the product of magnetic field lines and area of the loop, that is perpendicular area of the loop. Okay, so look at it. SI unit of magnetic flux is Weber, which is Tesla meter square. Tesla is unit of magnetic field, and the meter square is the SI unit of area, right? So look at the different cases of magnetic flux. What will happen when area vector is parallel to the field or perpendicular to the field and making certain angle to the field? Look at the first case. When this area vector is parallel to the magnetic field lines, the magnetic flux passing through, I'm not talking about the loop, I'm talking about the area vector of the loop. Okay, area vector of the loop is parallel to area vector of loop is denoted by A, and the magnetic field lines are denoted by B here. So these are parallel. When they are parallel, the angle between these two will be 0, and in this case magnetic field lines passing through this surface of the loop will be maximum, which is BA. Maximum flux will be passed when the angle between area vector and magnetic field lines is 0. When it is perpendicular, there will be minimum flux, right? There will be no induced current. As we have discussed earlier, when the angle between area vector and magnetic field lines is 90 degree, then total flux passing through this area will be 0. So this is the minimum case. If angle is between 0 to 90, then the magnetic flux will be BA cos theta. Okay, so based on these discussions, we can now define Faraday's law of induction. So EMF. So EMF is denoted by E, and it will be proportional to, induced EMF is proportional to number of turns, these turns of the loop, and a rate of change of flux. So induced EMF will depend on two things. One is number of turns in the coil, and the second is change in magnetic flux, which is phi, rate of change in magnetic flux. If they are changing fast, what will happen? Induced EMF will be more. If number of turns are more, induced EMF will be more. So to increase the value of induced EMF, what you can do? You can do two things. Either you can increase number of turns in the coil, or increase the rate of flux, magnetic flux, or you can do both. Okay. So in this expression, there is a minus sign that can be explained by Lenz's law. In next slides, we'll talk about Lenz's law. Okay. So an induced EMF in a wide loop or coil has a direction such that the current it creates produces its own magnetic field that opposes the change in magnetic flux through that loop. This law comes from the law of conservation of energy, because energy should be conserved, right? So when there is a change in magnetic flux, the opposing magnetic field will be produced because of induced EMF. Okay, this is the Lenz's law. So if the magnetic field is increasing, the induced current will produce a field in the opposite direction, that is decreasing. If magnetic field is decreasing means if you are taking away a bar magnet from coil, that is magnetic field is decreasing, right? And induced EMF will be in such a direction, it will increase the field, right? If you are taking towards a loop, then what will happen? That means it is you are increasing magnetic field, and induced magnetic field will be in opposite direction, which decreases the field. Okay. Direction of the induced current is given by right hand rule, and look at here what is the right hand rule is if induced magnetic field is in the direction of your thumb of right hand, the induced current will be in the called fingers, these fingers. Okay, this is direction of induced current. Okay, so Lenz's law is consequence of conservation of energy, as we discussed earlier. Look at here, side figure, increasing magnitude of B, because you are moving this magnet towards this loop, closed loop. So direction of current is anti-clockwise, and direction of induced magnetic field. I'm not talking about the external magnetic field. External magnetic field means magnetic field created by this bar magnet, and because of induced current, there will be induced magnetic field, and this will oppose the external magnetic field generated by this bar magnet, right? It can be shown in next figure. Look at here. This is the north pole of the magnet, external bar magnet. It is producing a magnetic field, and at the same time, induced current also generate a north pole which oppose this field. Look at here, direction of forces of these two magnetic field are trying to cancel each other. That's why we have a negative sign in the Faraday's law of induction. Okay, that's all for today.